selectively picks signals for local use. Demultiplexer demux highway off-ramp separates colors back to individual fibers. OTN, Optical Transport Network, OTN is often called the digital wrapper. While DWDM provides the lanes of light, OTN provides the shipping containers that sit inside those lanes. The problem it solves, DWDM alone is blind, it doesn't know if a signal is healthy or if it's failing. OTN wraps the data in a frame, standard G.709, that includes a header for management and a footer for error correction. Key components: OPU, payload unit where the actual data, Ethernet, fiber channel, etc., sits. ODU, data unit handles the routing and switching of the data. OTU, transport unit the final wrapper that adds forward error correction, FEC. OTN, Optical Transport Network, defined by the ITU-T G.709 standard, is often referred to as the digital wrapper. It was designed to provide the same management and reliability of legacy SONET/SDH networks but at the massive scales required by modern DWDM, dense wavelength division multiplexing, systems. If DWDM is the physical highway, OTN is the standardized shipping container that ensures the cargo, data, is protected, monitored, and delivered correctly. Key features of OTN Universal Container: OTN can wrap any type of traffic, Ethernet, storage, fiber channel, IP, or even legacy SONET into a single frame format without changing the original data. Forward error correction, FEC. This is the most critical feature. It adds mathematical check bits to the data, allowing the receiver to detect and fix transmission errors caused by noise or long distances. This extends the distance light can travel without needing expensive regeneration. Tandem connection monitoring, TCM. OTN allows multiple operators to monitor a signal as it passes through different network segments. This helps pinpoint exactly where a fault occurred in a multi-provider journey. Scalability, OTN supports massive bandwidth, with standard units like OTU for 100 Gbps, and beyond, OTU-CN for 400 G+. OAM, operations, administration, and maintenance provides deep visibility into the health of the optical link, including signal quality and trace identifiers to prevent mispatching. OTN frame structure. The OTN frame is organized as a matrix of 4 rows by 4080 columns. This structure is processed row by row, from top to bottom. The frame consists of 3 distinct sections, 1 overhead, columns 1 to 16, this is the shipping label of the container. It contains the management information needed to route and monitor the frame. FAS, frame alignment signal, helps the receiver find the start of the frame. OTU overhead, contains section level monitoring, and the trace ID. ODU overhead, contains end-to-end path monitoring and TCM bits for segment monitoring. OPU overhead, contains information about the type of payload being carried, example Ethernet versus fiber channel. 2 payload, column 17 to 3824, this is the cargo bay. This area contains the actual client data. Because the payload is so large compared to the overhead, OTN is extremely efficient, the overhead tax is very low compared to ATM. 3 forward error correction, FEC, columns 3825 to 4080, this is the security seal at the end of the container. The last 256 columns are dedicated to FEC using complex algorithms, like Reed-Solomon. The receiver can correct bit errors on the fly. This significantly improves the signal-to-noise ratio, SNR, allowing for higher speeds over longer fibers. The OTN hierarchy, the digital wrapper layers, OTN is built in layers, each wrapping the previous one. 1 OPU, optical payload unit, adapts the client signal, example mapping a 100G Ethernet signal into the frame. 2 ODU, optical data unit, adds the path overhead for end-to-end monitoring and switching. 3 OTU, optical transport unit, adds the section overhead and the FEC. This is the final frame that is converted into a specific color, wavelength, for the DWDM system. Summary table. Feature description. Standard ITU-T G.709. Primary goal: efficient transport and management of high-speed optical signals. Key advantage: FEC allows for longer distances and higher speeds, 100G/400G+. Efficiency much higher than ATM, very low overhead to payload ratio. How they work together: the modern stack. In a modern telecom network, OTN and DWDM work as a team. This combination replaced the older ATM over SONET model because it is much more efficient. The comparison: ATM versus OTN/DWDM. Feature: ATM, old school; OTN/DWDM, modern. Unit of data 53 byte cells, multi-gigabit frames, overhead 10%, cell tax, very low, highly efficient, error control detection only, HEC, correction, FEC, can fix errors on the fly, speed max 10 Gbps, 400 Gbps, 1.2 Tbps per wavelength. Purpose: mix voice/data at small scale, high capacity backbone for the whole internet. Key advantages of the OTN/DWDM pair: forward error correction, FEC. This is the magic of OTN. It can detect and fix bit errors caused by long-distance travel or signal noise. This allows light to travel thousands of miles without needing to be reread by a computer. Transparency, OTN can carry any type of traffic, Ethernet, legacy SONET, or even ATM, without changing the data. Grooming, just as ATM bundled virtual channels into paths, OTN can groom several 10G signals into a single 100G shipping container to save space on the DWDM highway. Modern applications in the modern digital landscape, the combination of OTN, Optical Transport Network, and DWDM, dense wavelength division multiplexing, serves as the unseen foundation of the Internet. While consumers interact with IP and Ethernet, OTN and DWDM provide the high-capacity, long-distance infrastructure that makes global connectivity possible. Here are the primary modern applications: 1. Hyperscale Data Center Interconnect, DCI. Cloud giants like Google, Amazon, AWS, and Microsoft operate massive data centers located hundreds of miles apart. They use OTN plus DWDM to link these facilities. The application: synchronizing databases and performing real-time backups, disaster recovery. Why OTN plus DWDM? These companies need massive pipes, 400G or 800G per wavelength. DWDM provides the raw capacity, while OTN provides the performance monitoring to ensure no data is lost during transit. 2. 5G mobile backhaul and midhaul 5G networks require significantly higher bandwidth and much lower latency than 4G. The application: carrying traffic from thousands of 5G small cells and towers to the core network. Why OTN plus DWDM? Low latency. OTN switching is faster than traditional IP routing for moving massive amounts of data. Slicing. OTN allows operators to slice a single fiber wavelength into dedicated channels, one for high-speed mobile broadband and another for ultra-reliable low-latency communications, like autonomous driving. 3. Submarine cable systems. Undersea cables are the backbone of the world, carrying 99% of international data. The application: connecting continents, example the Maria cable between Virginia, USA, and Spain. Why OTN plus DWDM? FEC, forward error correction. Over thousands of miles of underwater fiber, signals degrade. OTN's advanced FEC is the only way to fix the signal at the receiving end without having to place electronic regenerators on the ocean floor. Spectral efficiency. DWDM allows operators to squeeze the maximum possible terabits out of the few fiber pairs available in a multi-million-dollar cable. 4. Government and research networks. High security environments and scientific research, like CERN, generate massive amounts of data that must be transported securely. The application: moving petabytes of Large Hadron Collider data to research universities globally. Why OTN plus DWDM? Encryption. OTN supports wire speed encryption, where data is encrypted at the ODU layer. This is more secure and faster than software-based encryption, IPsec, because it happens at the hardware level without slowing down the traffic. 5. Wholesale carrier services. Carriers, like Lumen or Zayo, own the fiber and rent it out to smaller ISPs or private enterprises. The application: providing private line services. Why OTN plus DWDM? Transparency. A customer can hand the carrier an Ethernet signal, a fiber channel signal, or a SONET signal. OTN wraps it without looking at the contents, ensuring the customer receives exactly what they sent on the other end. Service level agreements. SLAs. OTN's built-in overhead allows carriers to prove to their customers that the line had 99.999% uptime and 0-bit errors. Summary: evolution of the everything network feature. ATM, the old goal; OTN plus DWDM, the modern reality. Speed 155 Mbps, 10 Gbps, 100 Gbps, 80 terabits. Efficiency. High cell tax, 10%. Extremely efficient, 1% overhead. Scalability. Complex to scale. Modular, add a wavelength to add capacity. Main use: integrating voice/data, fueling cloud, 5G, and global internet. The process of moving data from a client, like an Ethernet switch, onto a DWDM wavelength involves a multi-stage nesting process. It is best to think of it as a logistics operation: packing, mapping, sorting, multiplexing, and shipping, transport. Mapping client signals. The wrapping process: the first step is taking gray light signals, standard short-reach signals, from a client and wrapping them into the OTN structure. This is known as GMP, generic mapping procedure. Step 1, client to OPU, optical payload unit. The client signal, example 100G Ethernet, is placed into the OPU container. The OPU handles rate adaptation, ensuring that if the client's clock speed is slightly different from the network's clock, the difference is managed using stuffing bytes. Step 2, OPU to ODU, optical data unit path overhead is added. This allows the network to monitor the signal from end to end, source to destination, for errors and performance. Step 3, ODU to OTU, Optical Transport Unit Section Overhead and Forward Error Correction, FEC, are added. This is the final digital frame, ready to be converted into a specific colored laser frequency. Multiplexing multiple OTUs, the grooming process. In many cases, a single DWDM wavelength has a capacity of 100G, 400G, or even 800G. If a client only needs 10G, sending one 10G signal per wavelength would be a waste of fiber capacity. OTN uses time division multiplexing, TDM, to solve this. The ODU multiplexing hierarchy: lower speed containers, lower order ODU, are groomed into higher speed containers, higher order ODU 0, 1.25G, or ODU 2, 10G, signals are combined. They are mapped into a larger ODU 4, 100G, or ODU-CN, 400G+, container. Each smaller signal is assigned specific tributary slots, TS, within the larger frame, similar to how passengers are assigned specific seats on a plane. Transmission over DWDM: once we have a high-speed OTU frame, the digital wrapper is complete, it is handed over to the DWDM layer for physical transport. One wavelength assignment: the OTN transponder uses a tunable laser to assign the OTU frame to a specific frequency, example 193.1 Thz. 2. Optical multiplexing: this specific color is sent into a DWDM mux, where it joins 80 plus other wavelengths on a single fiber. 3. Photonic transport: the combined beam of light travels through EDFAs, amplifiers, and ROADMs, optical switches. The OTN data remains encapsulated inside the light wave, protected by its FEC security seal until it reaches the destination. Summary of the logic to visualize the flow: follow this hierarchy: payload, the actual data, the cargo. OTN ODU/OTU, the digital management and error correction, the shipping container. DWDM wavelength, the specific color of light, the truck/lane. Fiber optic cable, the physical medium, the highway. Level unit key function mapping: GMP/OPU adjusts data rates to fit the OTN frame. Packs multiple small signals into one big multiplexing ODUJ/ODUK container. Adds FEC and assigns a specific color for transport OTU lambda, the fiber.